I'm paying good money.
You gotta sap up as much electric as you can.
I'll get on, no problem. I'll get you a price. I'm going back and doing the old stuff.
Some programs too.
I know, I have, the C, my first class, I had a big project and then two slightly smaller projects, and I also have a Java project. And I'm working on all three at once.
I have computer science 2 class, assembly, and Java.
All this semester?
No, I was thinking of taking off one semester.
Computer science 2, the only thing that takes a while is like the big project. Because he has like a big project that takes, that's like the only thing that takes a lot of time.
Or not,
Because that was the one we did, that was like there you go, challenge.
I don't wanna hurt you and
C++ is easy because you get like, you get 200% education.
I already did that. I think it should
Okay. So what do you have left?
Java, high school, computer science,
Computer science 2 is easy, I haven't taken assembly yet, that's supposed to be.
Well, that's not the full Java and assembly.
I think Java and computer science too.
it's a better way to do that. Or I make or something. Java. Which is pretty interesting.
That's, I don't think I'm gonna try it, but I was.
It's just a way to separate the different. Yeah, I feel like from assembly, calculus,
Calculus too.
Yes, sir.
The model.
Nobody ever says I like calculus.
I didn't dislike it. I liked it. It was just, it was the hardest math class I've taken, but I still liked it. But then again, I'm weird. I like math.
Actually, it depends on the instructor who teaches you.
What's that?
Completely depends on the instructor who teaches you.
Well, that's true.
Yeah, because calculus 5, it could be really good, like, or else you could really hate it.
But yeah, it was, I mean, I had to spend hours, going just because the concept, it was there, but then applying it, well, I think I understand it, then you try to apply it, well, maybe I don't quite understand it.
It's very
It's because it takes 15 steps, and if you change one step midway, you're like, how do I solve this?
Is calculus 5 more difficult than calculus 3, right? Calculus 2 is difficult than calculus 3.
Oh yeah, much harder than 3.
Right? That's what everybody says.
Calculus 2 is the first math where it's not using, it's no longer introducing. So what you can do now, it's like actually using it. Like everything that you calculus 2, I think is
all the concepts you already learned. And now, because like if it says just like for instance, prove to someone.
the ways that they're actually intended.
You don't have the definition so you just say, okay, well, I know the fact that.
So it's like, I think
so that's why you have to keep auto yeah, because I know sometimes it's easier just to use the direct proof instead of case. But sometimes you can't use that.
this you do.
So when you can't,
I've changed.
Okay guys, so what we're going to do today is we're going to finish up our proofs with the floor and ceiling, and then we're also going to take a look at indirect proof methods, okay? And then don't forget guys, by Monday, make sure you guys have assignment 5 for me, and if you guys have some questions, I'll be happy to answer whatever I can. Okay. So last time we went through the definition of what floor and ceiling were. This is our definition of floor, okay? So remember guys, for any real number x, the definition that we're going to utilize is that x rests between two integer values, okay? Such that it could be equal to n, but at most it could be n minus 1 for the floor of that, or n plus 1, excuse me. And then for the ceiling function, okay, that there exists some real number that the ceiling of x is between these two integer values, it could be the maximum, okay, but it can't be the minimum value for this, okay? And we're going to utilize these definitions today to be able to do some proofs involving floor and ceiling, okay? So, last time I think we did our div mod, and we did like our quotient remainder theorem, and that sort of stuff. So today we want to go ahead and actually implement this. So, the first proof we're going to look at is we're going to use a direct proof to verify that if for some reason I took the floor of x minus 5, where x is a real number, that's equal to the floor of x, and then minus 5 from that. Okay? So before we do anything with this, let's just make sure that this statement's valid. Okay? We don't want to go through and prove this if it doesn't even work. Okay? So, Andre, give me a real number.
5.
Give me a real number that's not an integer.
6.1.
Okay, 6.1. Thanks, Andre.
Okay.
So, floor of 6.1 minus 5 hopefully is equal to the floor of 6.1 minus 5. Now, this is going to be 1.1 inside the parenthesis. Guys, what's the floor of 1.1?
1.
Over here, the floor of 6.1 is 6 minus 5. So at least for a very basic trivial case, it looks like it works, right guys? So we don't necessarily have any reason to doubt it yet, okay? So does that make sense, guys? Always go through in real life, okay? Now in math life, you guys know I'm going to make it work no matter what, because I wouldn't just give you a problem that you could just do that easily and then just get 10 points for that. Sorry, okay? So let's go ahead and do our proof, okay? Let's start by defining some variables. We obviously need to define a real number, okay? But we're also, because we need to use the definition of floor, we're also going to define an integer n, okay? Just because we need the definition. So here's what we're going to do. So let's let x be an element of real, and let's let n be an element of the integers, okay? And then in our brackets, arbitrary, but particular, yay. Now, this is one of those types of problems where we don't have a definition for real numbers, we don't have a definition for integers. What's the only definition that we really have? The definition of floor, right? So let's just use the very definition of floor, okay? So, we know that there's some integer, okay? So, there exists some integer n, or there exists n, such that the floor of x is equal to n, right guys? We know that that has to exist, okay? We don't, I mean there's no doubt about that, okay? Like if I took the floor of 4.2, that's 4, it's an integer, okay? That's the very definition, the very nature of the floor function, okay? Now we can use the floor function, okay? So by definition of floor, this animal right here, couldn't we rewrite this just as this right here? That's the this guy right here. That's the very definition of the floor. So that's going to be n less than or equal to x less than n minus 1. Okay?
Plus 1.
Plus, I keep doing that. Why do I keep doing that, Art? I don't know.
Maybe you didn't have a beer.
I know, I really need some more beers. Just I didn't have enough at lunch. I didn't have any, unfortunately.
That's definitely not enough.
I know, that's right. The ceiling of beers, not the floor. Oh, that's funny, we're in a math class. Alright, now, I'm trying to show this true for the floor of x minus 5, right? So guys, think about a compound inequality, alright? Because I'm looking to prove this for x minus 5, couldn't I legally, and algebraically, couldn't I subtract 5 from all 3 of the parts from this? Okay, for those of you guys that have worked with, the interval of convergence, you know that this is a typical type of compound inequality you have to work with. Okay, so n minus 5 less than or equal to x minus 5, and that's going to be less than n plus 1 minus 5. okay? And that's just by simple subtraction, okay? And everybody here agrees that's true. Like if you plugged in the numbers 2, 2.5, and 3, no matter what, if you subtracted 5 from all three of those, it would still be a true inequality, okay? So that's just by subtraction. Now, what can we say about this whole mess right here if I wanted to go back and reuse the definition of floor again? Okay, so let's just go ahead, go backwards from the definition of floor. Okay, so this is one of these where somebody kind of has to show you guys at least initially how this works. Okay, but does anybody think they might know what this whole animal could become if we kind of look at it like this? Anybody want to have a guess? Or? Well, this, if I had the floor of x equals n, and then I subtracted 5 from everything, right? Wouldn't this be the same thing as the floor of x minus 5 now? Okay? Because now, isn't this the exact same thing, but instead of x, we just substitute that with x minus 5, right? Like if I had a minus 2, I would just have an a minus 2 in the middle of that, okay? So it's basically we're subtracting 5 to make it fit the definition of floor. Okay. What is that equal to? Because the floor of x is equal to n up here. So what should this be equal to? Anybody think they might have a guess? N minus 5. Nice job. So basically, all we did was we just used the definition of floor to be able to subtract 5, and just to write it in that form. Okay, does that make sense to everybody, guys? It might be difficult to see, but we're just using the definition of floor to be able to work this. Okay? Now, I'm almost done, right? What I'm trying to show that this animal, x minus 5 floor, equals floor of x minus 5.
But you already showed that.
Oh, I did! What, and James, what do I know about the floor of x? What is that equal to?
N.
And couldn't we just substitute floor of x in for n? And we're done, right? Guys, check this out. N up here, we'll just pull some magic, is equal to the floor of x. So we get the floor of x minus 5 equals the floor of x 5 less than that. And that's just a substitution, right, guys?
Subtraction just turns into the floor of x minus 5.
Right. This whole statement right here is the very definition of floor of x minus 5, not just floor of x.
We can do that because we set the floor of x to equal n.
Correct, right? Okay. And it's some integer, right? So, and that's why this is completely legal, okay? We're basically just subtracting or adding what's inside there to make it true. That's all we're doing, guys. It's not meant to be too difficult. Okay. Questions, guys? We'll finish it off in a second, but I want to make sure at least the algebra component's okay with this. Okay? Guys, we could just say, thus by above, the original statement is true. Okay, I mean, this is the definition of floor, so by above, statement is true. Or valid, or whatever you want to say. I'll just say true. Guys, these are actually fairly simplistic proofs. I know for some of you guys it's like abstract as to where this is coming from, but basically we're just going ahead, using the definition, modifying the definition, and putting it back into the original form. Okay? So any questions, guys, before we try sealing proof? Okay? I think once you have one of these, most of them look the same. Okay? Like for instance, okay, the second example we have, okay, is that if I have any integer, and I should have defined m to be an integer, so let's do that first. Okay? So, for any integer m, the ceiling of x plus m is going to be equal to the ceiling of x, and then plus m. Okay? So, this time, instead of using the definition of floor, we're going to utilize the definition of ceiling. And guys, to use the definition of ceiling, you have to have a real number x and an integer n. Okay? So let's define those. Okay? So we start by saying, let's let x be an element of the real numbers. Let's let n be an element of the integers, okay? And we do our arbitrary but particular stuff. Isn't it true, guys, that there must be some integer n that equals the ceiling of x, okay? I mean, if a ceiling function is greatest integer function, okay? So, there exists n such that n is equal to the ceiling of x. Okay, we know this. Okay. Otherwise, there'd be no such thing as a ceiling function. Okay. So, guys, what do you think the next thing we should do with this is now that we've defined that there's some integer n?
By definition of
Let's
ceiling.
use our definition of ceiling, right, guys? I mean, when we've defined ceiling, we have all the variables there. Let's just go ahead and use it, okay? So, our definition of ceiling, we would say that n minus 1 is less than x, which is less than or equal to n, okay? That's the definition of ceiling. Okay. So, there's no algebra so far with this, guys. All we're just using is definitions that we're given. Okay, so this is nice thus far. I don't think it hurts anyone's feelings. If it does, too bad. Does somebody have a suggestion as to perhaps how we can get to x plus n, based on what we did before? Go ahead.
Plus m on every little.
Yeah, on the sides and in the middle. Let's just use that rule of addition of inequalities. Okay, so Greg, I like your idea. So n minus 1 plus m